Hello everyone. Welcome to the experiment 3 to the introduction to microcomputer lab. In this particular lab, we're going to explore the KL MDK version 4.7 and the ARM version 7 architecture with addressing modes, memory access operations. We're going to explore the uses of assembly directives as well as the uses of data allocation directives. We'll also be practicing how to store the constants in memory and to use of data movement instructions. And finally, we'll also be learning how to use different addressing modes. Assembly level languages, assembly directives are special commands or instructions that are not executed by the CPU but provide guidance and information to the assembler during the assembly processes. These directives help in organizing the program, specifying data allocation, controlling the flow of assembly, and providing information about the program structure. Different assembly languages may have different directives, and they're specific to the assembler being used. Assembly level languages, assembly directives are the directives that are defines a data section named my data with read write permissions, and there's some other assembly directives that has been actually used in the today's experiment where you're going to explore area my code read only. This is an assembly directive that defines the code section named my code with read only permissions. Only you can make the processor can only read the instructions but cannot any kind of modifications into this. And then there is entry, which is also the marks the entrance of the entire program. It is a assembler directive specifying the entire point of the entry point of the program. Export start is an assembler that makes the symbol of starting the coding portion and visible to the linker. Start is actually visible to the linker. It is typically used to indicate the starting point of the program. So from that starting point, the processor will going to start executing your code instructions. And then the end instruction is actually marks the end of the program. It is an assembler directive that indicating the end of the source file. So in the end instructions, the processor will going to stop its execution of the instructions that has been actually given by you. Data allocation directives are the directives in assembly language or instructions are directives that are used to allocate memory for data storage. These directives specify how many memory should be reserved for variables, constants, arrays, and other data structures. The actual implementation and available directives depend on the specific assembly language and assembler being used. And data allocation directives are you can see in the screen that AVEQ 0x200100. This is the equate directive defining the symbolic constant AV with the value 0x200100. BVEQ is the another equate directives defining the symbolic constant of BV. So BV and AV is the constant that has been actually assigned by EQ. So these are the two constants that is actually assigning data into the memory locations. Constant in the memory, in assembly language, constants in memory are values that are stored in the memory locations, so and do not change during the execution of a program. These constants are typically declared using directives to reserve memory space and assign a specific value. Constants are useful for storing fixed values such as numerical values, strings, and that remain constant throughout the program execution. Common directives used to declare constants in memory includes buffer size, data underscore byte, word underscore constant, and d word underscore constant. D word means data word. And the variable type or the constant type is dd. For word underscore constant, the constant type is dw. DW, DD, DC, EQ are the variable name that has been actually used. Buffer size, data byte are the variable type that has been assigned. Data management instruction. Data management instruction in assembly languages are instructions that perform operations related to the manipulation, transfer, and organization of data. These instructions are crucial for handling data within a program and interacting with the memory. The specific data management instructions can vary between different assembly language and architecture, but they generally include operations such as loading, storing, moving, and manipulating data. So there are some examples of data management instructions in the assembly languages. The architecture we are using a ARM version 7. So architecture, this architecture have this sort of data management instructions like load and store instructions, load, LDR, store, STR, move instruction, MOV, move with immediate, MOVI, move wide, MOVW, MOVT, these are move wide, copy and transfer instruction, data conversion instructions, sign extensions, zero extension, convert to floating point extension. There is a different type of data management instructions that are available in the ARM version 7 architecture. Bitwise operations instructions like AND or XOR, NOT, data comparison instructions, CMP, test performs the bitwise AND operation, updating conditions flags without storing the result. Data manipulation instructions, bit rotations, rotates bits to the right to left, ROR and ROL, shift instruction, LSL, that shifts bits from left, right logically or right arithmetically. Load, store, multiple instruction, LDM, STM. Data addressing modes. Data addressing modes in assembly language define how the processor accesses or reference data for instructions. These addressing modes specify the location or source of the operands that an instruction operation operates on. Here are some common data addressing modes: immediate addressing mode, index addressing mode, and PC relative addressing mode. Immediate addressing mode is the mode that is specified directly within the instruction itself. The actual value is part of the instruction and there is no need to look up the value in the memory. The mode is suitable for small and constant value. Say for an example, MOVEAX10, which is actually going to load the immediate value of 10 into the register EX. Index addressing mode. In an index addressing mode, the effective address of the operand is calculated by adding a constant to the contents of a register. This mode is often used for accessing elements in arrays of data structure where the index is stored in a register. Add R1, R2, R3, add the contents of the register R2 and R3 and store the result in R1. This is the index addressing mode. PC relative addressing mode. In PC relative addressing mode, the effective address of the operand is calculated as the sum of the program counter and a constant. The mode is often used for branching instructions, accessing data located at a fixed offset from the current instruction. LW dollars and T0 $8 PC, which is actually going to load the value of the memory address, which is the PC, plus 8. It is going to add 8 into the register T0. Then there is register addressing mode. Register addressing mode is the mode that where the operand is the register. Operand is in a register. The instruction operates directly on the contents of the specified register. Fast access to the data direct already in the register. Add R1, R2, R3, where add the contents of the register R2 and R3, store the result in R1. So this is register addressing mode. So now moving towards the today's procedure of the experiment 3, where you're going to create a project and add the startup tm4c123.s file to the project, and then you're going to run the code, the initial code that has been given to you from 1 to 4. Step 1 to 4, you're going to run the code for the first time, and then you're going to enable the debug mode, and then proceed with each single step of the code in the debug window, like you have done in the experiment 2. In step 1 to 4, you're going to write down the following code, and you're going to go into the debug mode and check the value of the register, and after each step report any changes. In this value, just report the changed registers, which register has actually changed, and then you're going to answer the questions whether the assembler has changed the instructions of MOV and why, and stop the simulation debugger and change the add R2 R0 R1 and to add R2 R0 to 0x7654. and then rebuild the code and check if there is any kind of error. If there is any kind of error, explain why you see this error and how you can fix it. And step 5, you're going to write down the following code, and then you're going to do the same procedure to observe the register, and you're going to answer the questions from the also you're going to take the help of the memory window, where the memory address from step C, and report how the value of AV is stored in memory, and draw a memory diagram showing how the AV is stored in memory. And then you're going to answer all the questions like report the value of R0 after running LDR R0 equal to AV instruction, and report the value of the R1 after running move R1 and VB instructions. But the value of VB is stored in memory. Is it RAM area or ROM area? Check the address from step Z and draw a memory diagram showing how BB is stored in memory. And change the code to store to 0x123456 instead of 0x1234, and then draw the memory diagram showing how the new BB is stored in memory. Remember here one thing, you have to actually draw the memory diagram of VB. And then you're going to remove the code in define your area, data here, and then write the following assembly code in write assembly code here sections after removing the step 5, and then write down this code, and you're going to make the answer of the questions that has been given here. So for example, you're going to go to the disassembly window and check how the assembler has actually changed the pseudo instruction to PC relative indexing addressing mode, where the address of my number value is stored in the memory location. The number after @ is exact memory location. From the memory window, after entire memory address from the step C, and report the value state stored in the memory, and draw a memory diagram showing how the value is stored in the memory. And then report the value of R0 after running LDR R0 equal to my number instruction. Explain whether it is actual value of my number, of the address of the my number. And then report the value of the R1 after running LDR R1 and R0 instruction, where the value of my number is stored in memory. Check the address from the step Z and draw a memory diagram showing how my number, which is 0x12345678, is stored in memory. From the disassembly window, check how the assembler has changed the pseudo instruction LDR R2 equal to hello underscore text to PC relative addressing mode, where the address hello underscore text value is stored in the memory location. The number after @ is the exact memory location. From the memory window, enter the memory address from step I and report the value stored in the memory. Draw a memory diagram showing how it is actually stored in the memory, where the value of hello underscore text is stored in memory. Check the address of the step K and draw a memory diagram showing how hello underscore text, which is hello new line, is stored in memory. Find the ASCII code of the hello new line and compare it with the data in the memory. And then moving to the step 7 to 8, where you're going to run the code, the following code, and you're going to find the introductory part of the field and space directives, and you're going to explain the difference between step 6 and 7, the difference between using data allocation directives in code area and data area. And you're going to do this procedure, which is step 7 and 8, where you're going to write your assembly code here and write the following assembly code in define your data area AV fields 10 0xa1 and VB space 10. You're going to save the changes, build the code, and check there is any error, and debug the code in simulation, run the code in single stepping mode. Explain the difference between field and space, how the data is stored in the memory. And in step 9, you're going to execute this code, and you're going to compare the value of R2 after running LDR, LDRB, LDRSB, LDRRH, and LDRSH. For the lab report, you're going to follow the procedure of the document and complete the experiment. Explain all the questions in the document, step 1 to 4, 5, 6, 7, 8 for each line of code. And obviously, you're going to add figure to every observation of the lines. Thank you.